Hello, and welcome to Logic and Proof. This course is concerned with logic. As for proof, it is, of course, as we are in computer science, we are concerned with proof as can be done through some sort of algorithm. In this course, we will eventually see a number of different ways of performing proof relatively efficiently by a computer. But before we can get there, we need to look at least some theory. So your previous year's introduction to discrete mathematics will be very useful here. For this first lecture, however, trying to keep things gentle, we will work without mathematics. So what are we talking about with logic? We're concerned with statements, with assertions, in some language, which for this lecture will mostly be English. Medieval logicians, of course, were more interested in Latin, and today, for our mechanized logics, we will need some sort of formal language. The thing about statements is that they are either true or false. Others are meaningless. Now, meaningless is an interesting case where there are, in fact, three-valued logics where you have an explicit, undefined truth of value. If you want my personal opinion, three-valued logics are a waste of time. Certainly no one is studying them seriously in a computer science context. Nevertheless, you have at the very least the idea that you can write some sentence in English, say, which is simply nonsensical. It turns out we're not only interested in statements being true or false, it really is necessary to talk about the relationships between statements, statements implying other statements, or statements in relation to other statements, whether they can both be true at the same time, whether when one is true, another is true, and so on. So we get into these notions such as satisfiability, which is the possibility of a set of statements all being true at once, or entailment, where when a set of statements are true at once, some other statement is also required to be true. Historically, the reason people have studied logic is with the aim of modeling human reasoning. I would express some skepticism here. Certainly, people in the past who have tried to use formal logic to do common sense reasoning have been unsuccessful. There is perhaps what they call slow thinking, using our, say, human part of our brain, which conceivably uses actual logic. But most of what people do when they go about their day-to-day business has really nothing to do with logic at all. As I said, logic is concerned with statements typically true or false. Here, these are statements with a definite meaning. Now, black is the color of my true love's hair. Comes from an old folk song. It actually illustrates a lot of interesting issues connected with logic, including formal logic. So firstly, of course, to make sense of this, we need to know the meaning of words such as black, color, hair, and most difficult, my true love. Now, meaning for us is going to be very simple compared with the actual meaning of such words in natural language. But nevertheless, all of these words need to somehow have some meaning attached to them. Now, a thing like my true love is even more interesting. It is a so-called description. So an complicating things further, we have my, which is related to the speaker. You have to know who that is. There's the question of whether they have a true love. Of course, there is the very semantics of true love as opposed to maybe someone who is not your true love, even though they may be some other sort of love, etc. So the meaning of a description is in fact a very interesting tangent in logic, which turns out to be quite important in the real world use of formalisms, although not something we're going to go into depth here. Anyway, this particular statement, subject to the various provisos I've just mentioned, is something that is true or false, at least if the speaker has a true love, and if the true love has hair, incidentally. So these various other sentences that I show next on the slide are examples of things that are not statements. Questions, wishes, and commands are not statements, and they are not within the purview of logic. Now, dealing with fully elaborated statements as black is the color of my true love's hair is not very flexible, and we need variables in order to be able to make more general statements and more general inferences. So if, for example, we replace my true love by X, not a very romantic name, we have made a more general assertion, which is the relationship, I guess, between some person X and whether their hair has the color black. There is still a description here, I suppose, because we still have the question of whether X has hair or not. If we replace that in turn by simply Y, so black is the color of Y is now simply the relation, or the property rather, of being black. And finally, if we replace black by a variable as well, we now have the color of relation. So this last is a relation involving two arguments. The one above, if you like, the property of being black, is a relation with one argument. In certain contexts, so in like with the Prolog programming language, which has some strong connections to our subject matter in this course, you can use statements that contain variables in order to express questions. So something of the form black is the color of Y can be interpreted as the question what things are black. And as I already said, we normally do not work with questions. But if we have a statement, black is the color of Y, and prove this statement while exhibiting a particular thing for Y, then we have answered that question. The moment you introduce variables, you need to do something about the meanings of those variables. So for this we use a map called an interpretation. Simply a function from variables to their meanings. Now, as I said, meaning for us will be very simplistic. So here, if I map Y to col, where col is presumably some built-in thing, so that we already know the meaning of col, then this is simply the syntactic transformation, if you like, that Y should be replaced by col. And if we do this, then black is the color of Y becomes true. If, on the other hand, we replace Y by strawberries, then we are making that statement false unless they are truly inferior strawberries. We are interested in a special class of statements called the valid statements. These are the statements which are true in every interpretation. As you might imagine, valid statements are in a sense tautologies. They will be things like P implies P, X equals X, things of that sort, which no matter what interpretations you place on the variables in them, they always evaluate to true. One of the most important concepts in connection with sets of statements is satisfiability. And this is merely the question of whether a certain set of statements can be made true, every element of set to be made true by one single interpretation. So if it is possible, we call the set satisfiable, otherwise it's unsatisfiable. Now we have the two examples on this slide. In the first one, we have that X is a subset of Y and Y is a subset of Z, but somehow X is not a subset of Z. That is simply impossible, so it's unsatisfiable. More interesting is the second example. So suppose we have an infinite set where we have, on the one hand, the assertion that n is a positive integer, but also in the set that n is not equal to 1, not equal to 2, not equal to 3, and so on for all the possible positive integers, then clearly it is impossible for all of those things to be true at the same time. So if n is a positive integer, then it will be included in these other things that n is not equal to, and there is no way to make them all true at the same time. Although interestingly, any subset of this set, so removing just one element from this set, makes it satisfiable. From satisfiability, we get the notion of entailment, also called logical consequence. So here we say that a set entails A if every interpretation satisfying S also satisfies A. You might be tempted to call this implication, but please don't. It is something slightly different because we're talking about interpretations. Nevertheless, and this comes from our previous two examples from the previous slide, if X is a subset of Y and Y is a subset of Z, all interpretations that satisfy both of those things also satisfy X is a subset of Z. So that entailment holds. As for the second example, if I know that n is not equal to 1, n is not equal to 2, and so on, then it follows that n is not a positive integer. Whereby it follows, I mean that any interpretation satisfying the infinite set of assertions on the left must satisfy the assertion on the right. Now, you may have noticed a little pattern here relating these two examples of entailment to the previous examples of unsatisfiable sets on the previous slide. And indeed, we find that S entails A if and only if not A joined with S is an unsatisfiable set. It's also true that if S is unsatisfiable, then S entails absolutely any formula A. That should be obvious because there is no interpretation satisfying S, and so vacuously A holds in every one of those. Finally, A is a valid formula, or we have already seen that a valid formula is one that holds in all interpretations. Now we see how we can write it, and now we see that a valid formula is one that is entailed by the empty set. And this is equivalent to the set containing the negation of A being unsatisfiable. All of these properties hold immediately, essentially from the definitions. Now it's time to make the transition to proof. What we've been doing so far is talking about interpreting variables by constants and what appears to be enumerations of things. But how can we prove that some formula A is valid? Now, there are some interesting cases in mathematics, for example, of Fermat's last theorem, which had been tested for billions and billions of cases and come out true every time, and yet a mathematician can see that only as a hint that the Fermat's last theorem in this case might be a theorem, but not an actual proof. And so, in the case of Fermat's last theorem, a very elaborate proof finally emerged. In the case of other questions, such as the Riemann hypothesis, an immense number of cases have been checked, but all they give us is a hint that we should keep looking for an actual proof. So what is a formal proof? Well, in mathematical reasoning, mathematicians make definitions. They perhaps work with a primitive axiomatic basis, and then they deduce using careful arguments, they deduce theorems. A formal system is a model of mathematical reasoning. So to this extent, I agree with the old idea that logic is about thought. So it is trying to model at least mathematical thought. So in a formal system, we have things called theorems. These will be special statements that are inferred from a small set of axioms using selected rules of inference. If we are working formally, a formal system will necessarily itself be a mathematical object, and the entire field of metamathematics has to do with studying the mathematical properties of formal systems. So what is an inference rule? Very simply, it delivers some conclusion, and in order to do that, it needs to be given one or more premises. Now, where do these come from? A hint. They could come from certain entailment relations. So if I have any particular entailment where some n formulas, A1 up to AN, entail B, that suggests an inference rule. That is, we know that whenever A1 up to AN are true, and that any interpretation making them all true, that same interpretation makes B true. It then follows that if A1 up to AN are valid, meaning true in all interpretations, then B will also be valid and true in all interpretations. And therefore, we could make an inference rule based on A1 up to AN deducing B. Now, just because we can do that, it doesn't mean that we're going to do this with every possible entailment, because, of course, that we have unlimited entailments. But a reasonable formal system has very few inference rules. So one will select them very carefully. So there's a tremendous process of refinement and adjustment in creating a formal system. And we will look at a number of formal systems in our future lectures. Finally, the theorems, the formal theorems of our formal system, will be built up in an inductive way from the axioms. That is to say, all the axioms trivially count as theorems, and now take any existing theorems, supply them to any inference rule that matches up with those theorems. So typically the inference rule will expect things of a particular form. So you choose a suitable inference rule that is appropriate for the theorems you give it, and this rule will give you yet another theorem, and so we go on. Now, we will normally have variables in our inference rules. Indeed, if we didn't, we would have a pretty primitive system indeed. So here is an example. One might imagine such a rule of inference existing in a special calculus for set theory, though this is only an example. Now, it's worth stressing, and this is a general property of deductive logic in general, that the correctness of proof is purely a matter of syntax. So, in order to check a proof, you basically check that it has been written out correctly, that all the rules are officially rules of your calculus, and all the axioms are really rules of your calculus. They have all been written out correctly. They have all been applied correctly. Any preconditions of these rules have been adhered to. And in checking whether a rule is correct, there are a number of things that are totally irrelevant, such as whether we like the conclusion, or even whether the conclusion is true. So a proof could be a valid proof, a correct proof, and yet have an invalid conclusion. That would be a strong hint to us that perhaps one of the premises was false, or maybe that the formal system itself is unsound. Those things are possible. Nevertheless, the proof will be correct provided it obeys all the rules of the formal system. And crucially, as we are computer scientists, we don't care who or indeed what created the proof. So in particular, a machine can create the proof, and perhaps some other machine, perhaps in an adversarial mode, can check the proof. So if you do not trust the person who created the proof, or the system or organization that created the proof, you can examine the document that they gave you and verify it, rather in spirit like verifying a digital signature or verifying a digital certificate. You can validate the proof you were given. And this is very much simpler than the task of finding the proof in the first place, which in fact turns out to be undecidable. Now, we are concerned in formal systems with a crucial property known as consistency. This is related to satisfiability. So remember, a formal system is a mathematical object that defines a set of theorems for whatever language it is concerned with. Now, it may happen that every statement is a theorem. Now, you might say, why? Who in God's name would set up a formal system in which it declares every statement to be a theorem? And the answer is, nobody does it on purpose, but many, many people have done it by accident. So if it turns out that every statement of your language is a theorem of your formal calculus, then your formal calculus is inconsistent. And that is a shame, and you need to go away and fix it. Now, this is clearly related to the notion of satisfiability, or rather in its negated form, unsatisfiability. If you have an unsatisfiable set of axioms, and you connect it to any reasonable formal system, the result will be inconsistent, so you will get the ability to prove anything in your formal system. So satisfiability is the semantic counterpart of consistency. And we will see that many theorem-proving methods work by looking at a set of formulas and detecting their unsatisfiability. Now let's look at a little thing called Richard's paradox. It's really very clever. So our idea is to notice that there are many phrases in the English language that define real numbers. So if I to refer to the base of the natural logarithm. That is a number we know as e. That definitely refers to one particular real number. Or my other example, the positive solution of x squared equals 2, again, is one unique real number. We can now conceive of the set of all such phrases. It is, of course, infinite. And we can imagine this list being sorted. So there's some difficulties here. And incidentally, I'm not claiming this is a computational process. It is not. We are dealing with infinite numbers of things, but nevertheless, one can conceive of this set of phrases organized alphabetically. In fact, you need to organize them by their length first and then alphabetically. And when you do that, you will get a set of real numbers. This is the set of all real numbers expressible in English. Now we can define a new real number, a real number which will have before the decimal point just a 0, and after the decimal point we organize it so the nth decimal place differs from the nth decimal place of the number Rn. Those of you who are familiar with your computation theory will recognize this as a diagonalization. So we started with the purported set of all English phrases defining real numbers, and then suddenly we have written another English phrase which defines another real number that is not in the set that that already was meant to contain all of them. So we seem to have a contradiction. What's going on here? If you didn't like that, here is a simpler one, Berry's paradox. Here we're only concerned with integers. So consider the smallest positive integer not definable using 9 words. Well, a hint here, that sentence has 9 words in it. Now, there are many, many sentences in English that define various positive integers. So I have, for example, the number of atoms in the Milky Way galaxy is definable using 9 words and is a very, very large number. But the sentence in green above that has a slight problem that by definition it is a positive integer greater than itself. So what is wrong here, and what was wrong with Richard's paradox? In both cases we have a problem with the notion of definable, that previously definable was used, shall we say, in a relatively concrete way, but somehow we are using the thing we just defined to define something else and getting a contradiction. And because we're using the English language, it is slippery enough and ambiguous enough to allow this sort of contradiction to arise. So certainly one massive reason for using a formal language is to eliminate such ambiguities. The second big reason for us computer scientists is that a formal language can be manipulated by machine and using algorithms and code. Now, I would briefly like to conclude by surveying some of the formal logics out there, many of which you may have seen before. First, there's propositional logic, Boolean algebra. You will have seen it in a digital electronics course. You will have seen it in discrete mathematics. It is the world of and or not implies, if and only if, and indeed exclusive or, though for some reason maths books tend to ignore exclusive or. It's more of a hardware thing. You can actually do a surprising amount with propositional logic, as we will see later. It's decidable, and there are a number of very powerful procedures for operating on very large sets of propositional logic formulas. and not only to solve problems in hardware, but in much more general contexts. With first-order logic, we can talk about for all and there exists over a domain. You'll have seen it in discrete maths, and we'll have quite a lot on that in this course here. Already, our validity problem becomes undecidable, but we do have powerful proof procedures, and a lot can be expressed in first-order logic, an awful lot of normal mathematics. The next step is higher-order logic. Here, effectively, we are taking first-order logic and building in some set theory and some functions right into the logic itself. This makes a much more expressive formalism with, I have to say, a much messier meta-theory, but we, as computer scientists, are not that interested in meta-theory. What is important is that in higher order logic you can formalize a lot of things very easily. One point in particular, Mike Gordon of this computer lab proved during the 1980s that higher order logic is good enough to state properties of hardware devices at quite, not only at low levels of detail down to the transistor level, but also at high levels of detail up to the processor level, all with this one uniform formalism of higher order logic. Modal and temporal logics feature a tiny bit in this course, but they also have an important role in computer science more generally, mostly in connection with concurrency and making predictions about the future behavior of concurrent systems. Finally, there are type theories, a great variety of them. Typically, they are focused on so-called constructive mathematics. They are certainly an effective way of obtaining research funding. A lot of people find them fascinating, and they do seem to have a lot of potential for formalizing certain types of mathematical structures. All of the formalisms that I have just mentioned are important in the verification of problems in computer science. And that is it for today. Thank you very much for listening.